This Calc 2 lecture is on calculus with parametric curves. So, this section we're going to do two things. Number one, we are going to find slopes, and we are going to use these to actually write the equation of a tangent line to a curve at a point. And you should be thinking, well, yeah, I already know how to do that. Yes, you do, but not with parametric curves. And the second thing that we are going to do is find lengths, and by lengths I mean arc lengths of parametric curves. And this is going to allow us to find basically what you and I would think of as perimeter or circumference, that idea of some different shaped things, different curves. So let's focus right now on number one. What do we need to do to be able to write the equation of a line tangent to a curve at a point? You know you need this equation, which means you need a slope and a point. So our directions and the steps that we follow are below. To write the equation of a line tangent to a curve given parametric equations, we're going to do the following. We're going to take those parametric equations and we are going to change them into Cartesian equations. Then we are going to find the derivatives dx dt and dy dt of the parametric equations, which means we're going to need to use implicit differentiation. We're going to actually find the slope by doing dy dt over dx dt, which gives us dy dx. So this is your whole idea from Calc 1 about the chain rule. The only place people mess this up is they tend to sometimes do dx over dy, because notice what's on top. This is dy on top. So just be careful there. So I'm going to find the derivatives, and then I'm going to figure out the slope. All right, that will give me my slope. Then I need to find my point, and I'm going to do that using whatever t I am given, and then I will be able to write the equation of the tangent line using my y minus y1 equals m times x minus x1. So let's attempt to do one of these problems, because I don't think you're going to find them all that difficult. Remember what you need. If you're writing a line tangent to a curve at a particular point using these two parametric equations and this value of t to find your point, you again are going to go back to your point slope form of an equation of a line. So you're going to use your derivatives to find your slope, and you're going to use your t value to find your point. So hopefully you're comfortable with where we're headed, and let's start. So let's find the, first of all, let's find my actual, let's do what we did in section 11.1 and actually find the Cartesian equation first. And by the way, when you are doing the problems in your book, you don't need to do the whole second derivative thing as you're asked in the textbook, so ignore those directions. All right, if I'm going to find the Cartesian equation of these two parametric equations, you should realize by now that your two choices are: one, solve for t and plug in the other equation. Number two, square both sides of both equations. Now, I need to look for some identity that I am familiar with that has to do with secant squared t and tangent squared t. So let's go back to my basic trig and figure out what that relationship is. If I divide everything through by cosine squared theta, I'm going to come up with tangent squared theta plus 1 equals secant squared theta. And so if I'm looking for a relationship with both of these two things in it, it would be that 1 is equal to secant squared theta minus tangent squared theta. So I am going to do secant squared theta, or secant squared t in this particular instance, minus tangent squared t. So that has to equal, all right, remember, secant squared t is x squared, and tangent squared t is y squared. So I know this thing is 1, so I'll have 1 equals x squared minus y squared. You guys should recognize this as a hyperbola. I'll graph that a little bit later toward the end of the problem. But let's just keep in mind now that we have a Cartesian equation and that it is x squared minus y squared equals 1. All right, get down everything you want to. I'm going to erase, and then we are going to find our derivatives to find our slope and use our given t value to find our point. So, derivatives. Implicit differentiation. Dx dt will equal secant t tangent t dt dt. Everybody good? Those divide out. And dy dt is equal to secant squared t dt dt, divides out. So just once to again show you how this works, dy dt over dx dt would give us secant squared t over secant squared t tangent t So on the left-hand side, dy dt, again, I don't do that because I understand it, that it just gives me this. Whoops, I messed up someplace. Right here. This is just a secant t. All right, dividing out over here. I can divide out this secant t and one of those. So now I am looking at secant t divided by tangent t. I'm going to see if I can make that any simpler. Secant of an argument is 1 over the cosine of the argument. Tangent of the argument is sine of the argument over cosine of the argument, but if I am dividing by that, I would multiply by the reciprocal, so this would be cosine t over sine t. Simplifying one more time, and I will have that dy dt is equal to 1 over sine t. Now, yes, I could change that to cosecant t, but I am going to need to find my slope. Remember, one of your understandings of a derivative is the slope of a tangent line at a particular point on a curve. So I'm going to take this t value right here, and I am going to plug it in right here to that t. And so I will get my slope, dy dt, which is equal to my slope, will be 1 over the sine of pi over 4. So my slope that I'm going to use in my point slope form will be 1 over the square root of 2, or rad 2. So remember the two things that I need to write the equation of a tangent line to a curve. I need a slope and I need a point. So I have my slope. My slope is rad 2. So now I need to find my point. So let's get rid of this thing that's taking up so much space. And let's find my point. So you guys know how to find a point. You plug in a t, you find the x, you find the y, and there's your coordinate. So my t is pi over 4. So x is the secant of pi over 4. Y will be the tangent of pi over 4. So let's figure out what those values are. The secant of pi over 4 is the reciprocal of the cosine of pi over 4, so that's going to be the square root of 2. Tangent of pi over 4 is tangent of 45 degrees, or just 1. So guys, now I have my point. My point is square root of 2, comma 1. Those are my coordinates. So let's write my equation of my line. I have y minus y sub 1 equals, m was the square root of 2, right here, times x minus, y sub 1 was 1. X minus the square root of 2. So let's distribute. Rad 2x minus 2. Let's add 1 to both sides. So y will equal the square root of 2 x minus 1. So here is my equation of my tangent line to this curve at this point. Now, just to take a minute and think about the graph, I'm going to erase the left side over here and sketch my hyperbola. All right. So when I look over here, this has a denominator of 1, this has a denominator of 1. The x term is positive, so my transverse axis is horizontal. So everything's going to go on that axis. The center of my hyperbola is 0, 0, because neither the x squared nor the y squared has anything added or subtracted to the x. A squared is 1, so a is also 1. So I am going over 1 unit on the right and 1 unit to the left for my vertices. B squared also is 1, so the end of my other axis will be right there. So now let's draw my box. So here's my asymptotes. This thing is oriented horizontally, so let's see if I can draw relatively accurately here. Okay, so this equation down here is a tangent line to the curve at the point, the square root of 2, 1. So let me get some more hash marks here. So here's 1, here's 2, here's -1, here's -2, here's 2, here's -2. Okay, so the square root of 2 is between 1 and 2, so I'm going to label that right here, rad 2, rad 2. So my point is at rad 2, 1. So there's the point of tangency. So my equation has a slope of rad 2. So from here I am going up rad 2 and over 1. And, well, alright, I need my y-intercept. Here's my y-intercept. Might be easier to draw it that way. Let's see. Okay, there we go. So this is my line right here. This is my y equals square root of 2x minus 1. All right, just wanted you to see what it is that you are actually finding. So let's do another one. And this time we're just going to follow the directions. I'm not going to do anything extra. Again, we are looking for the line tangent to the curve at the point that I am given. So I'm not even going to figure out what kind of graph this is. I'm just going to write the equation of the line. So two things. I need my slope. First, to do that, I need the derivatives of both of my parametric equations. So I will have dx dt is equal to negative sine t dt dt, which divides out. And dy dx is equal to negative rad 3 sine t dt dt, which divides out. So now I am doing dy over dx and I want you to notice what's happening this time. Do you see that I am only coming up with a constant answer? My slope is the square root of 3. Guys, last time I had to take my value of t and I had to plug it into the t in this equation. I don't have to do that this time. My slope is just the square root of 3, no matter what point I'm at on this parametric equation. So the next thing I need to do is find my point. So I have a t, I have an x, I have a y, and an ordered pair. So t is 2 pi over 3. So x will be the cosine of 2 pi over 3. Y will be the square root of 3 times the cosine of 2 pi over 3. So pay attention to the fact that 2 pi thirds is in quadrant 2 with a 60-degree angle. So this value will be a negative 1/2, again because you're in quadrant 2. All students take calculus, so in quadrant 2 only sign is positive. In quadrant 3, it will be the square root of 3 times a negative 1/2, and so a negative rad 3 over 2. So my point, negative 1/2, negative rad 3 over 2. Let's write the equation of my line. Y minus y sub 1 is negative rad 3 over 2. My slope is the square root of 3. X minus x sub 1 is negative 1/2. So I have y plus the square root of 3 over 2 is equal to rad 3x plus rad 3 over 2. The rad 3's over 2. When I subtract that from both sides, gives me 0. So my answer is just y equals the square root of 3x. All right, get copied down what you need to copy down, and then we will move on to page 3. Page 3 is for you to try. So what I'd like you to do is just to write down the parametric equations and then pause the video and on your own notes or paper to see if you can find the equation of the line tangent to the curve. If you get stuck, come back and look at my work. So pause the video now, please. All right, welcome back. Compare your work to mine. Places that you may have messed up would be when you were finding your derivative. Hopefully you let the radical of t plus 1 be t plus 1 to the 1/2, and the derivative of the square root of 3t quantity to the 1/2. And if you forgot anything, it might have been to take the derivative of what was inside. Again, this time when you find your slope, it was a constant. Here's the work for finding your point, and here's the equation of the line tangent to the curve. So our first objective in this section is done. You were to write lines tangent to a curve at a particular point for parametric equations. Our second task in this section is finding the arc length. So this material here is a brief review of finding arc length in Calc 1. Hopefully you remember how we took a curve from some A to some B, and we were trying to find the length of that blue curve. And so we divided our curve into a bunch of little itty-bitty line segments. So the way they have it drawn right now, here's one, here's another one, and they eventually divide these line segments into smaller and smaller pieces. So for instance, you would have a teeny one here, a teeny one here, a teeny one here, and so on. You are adding up a whole bunch of these little bitty line segments. You recall our big idea in calculus that an integral will add up an infinite number of these, or as we approach an infinite number of these, in this instance, line segments, as they are getting smaller and smaller, our integral will do that for us. So this is the formula we came up with in Calc 1 for arc length when we had a curve that was given to us with Cartesian coordinates, x's and y's. So our job today is to figure out how to find the arc length of a curve that's defined parametrically. We are going to use a similar idea. We are going to make line segments from our parametric curve and make them smaller and smaller and add up an infinite number of those. So in other words, we're finding the limit as the number of those approaches infinity. So look at this particular curve. Here is one segment. So this would be defined as the difference in the y's and the difference in the x's in that particular parametric equation. So when we go to plug this into our regular old distance formula, instead of using x sub 2 minus x sub 1, since we do not have those variables, we're dealing with t's here, then I need to write this length of this particular curve as the difference, as the change in my x's over the change in my y's. Guys, I can write that parametrically as f prime of t, and this as g prime of t. So you can find your derivative, your arc length, using this formula. This is one segment, and plugging that into an integral from a to b. That's the length of the whole arc. So your whole curve, the entire thing, the integral from a to b. However, I prefer, just my personal opinion, to do this for one segment instead of writing out f prime of t, quantity squared, to think of that as dx dt squared, and this derivative as dy dt squared. So my entire arc length, as opposed to just one segment, would be the integral from a to b of the square root of dx dt squared plus dy dt squared. So again, this is the formula that I find easier to think about than this one, but it doesn't matter to me which way you think about this. Now, let's look at the actual definition of arc length. If your curve is defined parametrically by your two parametric equations, and you have some interval for t that has endpoints, in other words, we can't be going on to infinity. As long as the derivative of your first parametric equation is continuous and your second is continuous, and they are both not zero at the same time on the interval, and one more condition, C is traversed exactly once. That means you're traveling the path once. As t increases from A to B, so as you are going from the smaller value to the larger value, you're tracing the path once. Then the arc length is defined as this interval. And again, I like to think of this as dx dt quantity squared plus dy dt quantity squared. So again, if you're going to use our definition, the formula that I explained to you, the curve can't double back or reverse itself when you are going from A to B. That's what they mean by traversed exactly once. Second thing you need to know, you understand from the previous section from 11.1 that there can be more than one parametrization for a curve. If there is, it does not matter which one you use to find the length of the arc. That makes sense. If the parametrizations graph exactly the same way, then the curve length ought to be exactly the same no matter which parametric equations I use. Now, why is this helpful? Kind of what I hinted at the beginning. We can now find the perimeter of conics, such as how far around it is around an ellipse. Think solar system. You can find the perimeter of polar graphs, like Lee Mason's. Remember those things from pre-calc? Hopefully, because we're going to be doing them again in this chapter 11. And we can find the distance around such things as cycloids, and don't know how to say that word. Somebody who speaks French would probably be better at that than I would, but here you go. So let's actually do some work. Determine the arc length of the curve on the interval from 0 to 2 pi. Guys, I'm giving you an example at first that's really, really easy, and that we can verify the distance around the shape by using something we already know from geometry. So first thing that I need to do is take my derivatives. So the derivative of x equals 2 cosine t works out to be negative 2 sine t. The derivative of y equals 2 sine t is y equals 2 cosine t. So I plug those into my formula, step number 2, and I square both of them. And when I do that, I am going to get this equation right here. You are looking for some way to simplify what is inside there to find something you can take the integral of. So for instance, when I factor out this 4 that's in common in both of those expressions, I'm left with sine squared t plus cosine squared t. We know that that's a 1, and 4 times 1 is just 4. Square root of 4 is 2. Antiderivative of 2 is 2t, and I need to evaluate from 0 to 2 pi. So fundamental theorem of calculus, f of b minus f of a, and here is my answer. Now, that is all the work you would be expected to do, but I want to help you understand that this actually is the length around that particular curve. So you will not have to do this, but let's change these two parametric equations to a Cartesian equation. I am going to square both sides. I am looking at some relationship that I can find that's trig. So I'm going to take these two and add them together, which means I am taking these two and adding them together. I'm factoring out the 4 that I see in both of those. Because this is a 1, I get just a 4. You guys recognize that as a circle whose center is at the origin and whose radius is 2. So that's the shape that I have drawn right here. X squared plus y squared is equal to 2. Can't see your... And guys, you know how to find the circumference of a circle. It's 2 pi r. So the circumference of my circle is equal to 2 pi times my radius, which was 2. So my circumference is 4 pi, exactly what I got up here. Again, nothing in blue do you need to do. I'm just confirming with you that that's the actual arc length. So let's do one more that is a bit more difficult, and I can't confirm that with any geometric formula that I know from high school. determine the arc length of the curve on the interval, closed interval from 0 to 2. So I am taking number 1, my derivatives. Number 2, plugging them into my formula, squaring their sums. That gives me the square root of 4t squared plus t to the 4th. I'm factoring out this t squared that's common in both of those. The square root of t squared is just t. So get that much copied down on your paper. And let's come back and think about how, if we are going to integrate this, I need to use u sub. So I am going to let u be equal to what's underneath the radical, the 4 plus t squared. Integrating both sides of that equation gives me du is equal to derivative of 4 is 0, derivative of t squared is 2t. You guys know that this is really a du dt, and this is really a dt dt, and then when I move this dt over from this side, it moves over to here. So I have now a dt here. I have a t here. I see them both right here. So I need to divide both sides of this equation right here by 2, or multiply by 1/2, and when I do, I get 1/2 du, substituting in for t dt. So here's my 1/2, here's my du. I have u going in here, and here is my radical. Antiderivative there, add 1 to 1/2, I get 3/2. Divide by 3/2 or multiply by the reciprocal. The 2's divide out, so I get 1/3. Plug back in 4 plus t squared for u. Evaluate using the fundamental theorem of calculus, so I'm plugging a 2 in here, and then I am plugging a 0 in here. And you eventually come up with this exact answer and this approximate answer. Now, I want you to have an idea of what you are finding, because remember, your integral is only, your arc length is only from x equals 0 to x equals 2. So I am taking my two parametric equations, x equals t squared minus 1 and y equals 1/3 t cubed minus 2. I am solving this equation here for t. I will get t equals plus or minus the square root of x plus 1. I am plugging this in for that t right there, which gives me y equals plus or minus 1/3 the square root of x plus 1 cubed minus 2. So when I write that radical as an exponent of 3/2, this is the equation I'm looking at. You guys should recognize this as a shift up. You should understand that I am taking a expression and taking the square root of it and cubing it. And when you actually graph this thing, here is positive 1/3, the quantity x plus 1 to the 3/2 minus 2. And here is negative 1/3, quantity x plus 1 to the 3/2 minus 2. So you have figured out the length right here, either the exact or the decimal approximation of the length of that curve. So calculus is enabling us to find arc lengths of lots and lots of different shapes. All right, that ends the lecture on calculus with parametric curves.